Prochiral carbons possess enantiotopic groups or faces. Selective functionalization of one or the other of these groups or faces leads to a nonracemic amount of a chiral product. That's the situation you're looking at on this slide. And for this example, I just wanted to talk a little bit about the energetics of the reaction of one enantiotopic group or face versus another, and how you can think about prochirality in terms of reaction coordinate diagrams, for instance. So in this example, essentially what happens is a nucleophilic enamine is generated from proline and the starting material, and proline possesses a chiral center. As a result, we've rendered this intermediate of the reaction chiral. And because we're using only L-proline, we have only a single enantiomer of this chiral intermediate present in the reaction mixture. Let's represent this intermediate on the reaction coordinate diagram, not worrying about anything that happens prior to the formation of this intermediate. And I'll draw it in the center of the diagram so we can compare the energetics of competing pathways. If the enamine adds to one of the enantiotopic carbonyl groups, with curved arrows that look like this for instance, then we would have some kind of energetic pathway maybe that looks like this. As that transition state develops, we're developing a stereocenter on the carbonyl group that's getting added to. Now consider the situation if we add to the other enantiotopic carbonyl group from the same face. In that case, we're generating a stereocenter at the other carbonyl carbon. Because the stereocenter on proline does not change, the relationship between those two transition states, and certainly between the two products, is diastereomeric. Importantly, the diastereomers must differ in energy. Thus, the energies associated with one addition pathway must be different from those associated with the other addition pathway. And one of them must be more favorable than the other. So the way I've drawn it, the blue pathway is more favorable than the black, both kinetically and thermodynamically. The product is lower in energy, and the transition state is lower in energy. This is the origin of the selectivity of this process for the single stereoisomer of product. The energy to add to one carbonyl must be lower than the energy to add to the other. The key generalizable idea here is this idea of diastereomeric transition states. So if we want to selectively convert an achiral molecule A with enantiotopic groups, specifically into a product A prime, and let's say we want to get out the R stereocenter here, what we need to do is somehow render A chiral before the new stereocenter is set. One way to do this is to complex A with an enzyme which possesses a vast array of stereocenters already built in. And none of these stereocenters will change through the course of the reaction because the enzyme stereochemistry is set and isn't involved in the reaction. So what we would need to do first is complex A to an enzyme that's chiral, let's call it E star. Upon doing that, now the two possible products that could form, let's call them E star A prime R and E star A prime S, are now diastereomeric to one another. And this is very important because now the energies of, let's say, P1 for pathway 1 and P2 for pathway 2 are different. As a result, one pathway is selectively chosen over the other.